Good afternoon to all of you. So, in the last class, we looked at that, okay, your thermodynamics of your gas turbine. We started the thermodynamics of gas turbine. So, we went ahead with a structured, first we will look at that, okay, how the individual component, from the individual component, from the known values, how are we going to find out the unknown values of inlet and exit parameters. So, based on that, okay, we have a known parameter like isotropic efficiency. If we know that, okay, if we know the inlet parameter, inlet stagnation temperature, how will you find out that? So those things we looked at that in detail. Okay, so I had received some of the comments from you based on your last class. Okay, today I will start it out, but even you could have told me in that at the time itself, okay, so you want these other things and all, you could have mentioned it, so I can solve it. So if you have any issues now itself, you tell me, I can sort it out that. Okay, so today we will go ahead for certain problem solving. For example, okay, you keep your calculator with you. If I need an answer, please tell me that answer. Let us have a flight is going to fly with a Mach number of, okay, 0.8. Let us take atmospheric condition P as 1 bar and your T as 288 Kelvin. Do you know how to find out your P01 and T01? Even ρ01 also? Can you do that? Can you give me the value? This is from that we have discussed earlier. Your T01 by your TA is equal to 1 plus gamma minus, let us even, you can take it as a P0A, P0A, ρ0A. This one, 1 plus gamma minus 1 by 2 MA. You know the TA value, you can find out your T01 value, T0A value. Okay, same way your P0A also you can find out that. Whole to the power of gamma by gamma minus 1. So from that, you know the PA, you can find out the P0A. ρ0A, you can use the same relation, okay. ρ0A by ρA, it's going to be like your T0A by TA whole to the power 1 by gamma minus 1. Okay, using that you can find out, or otherwise, okay, what we can do is your ρ0A, is it this relation is right? Your ρ0A by ρA. What will happen? Okay, so that you look at that. Okay, this power and all you check it up very, or otherwise what we can do is P0A by your R P0A. We know that, okay, T is equal to ρRT, so that's going to be valid. Okay, so you know that R value as for air and all, if you know that, okay, that's going to be, already I told you last class, R bar divided by your molecular weight. R is the universal gas constant, mW is the molecular weight. So if you, for example, if you look at that R value for the air and all, 287 to or 286 joule per kg Kelvin, you can find out that. Okay, so even in last class itself I reiterated that, okay, these are some basic things you are going to apply in your this one, but the main thing is, okay, your speed of sound, your A infinity square root of gamma R T infinity. So here, whatever the your gamma value for the particular medium, don't put particular medium. So whether the gamma value is going to be diatomic or monoatomic or triatomic. Or triatomic. So if you look at your gamma value, that's last class itself I told you, it's going to vary between 1 and 1.67. Okay, the range of gamma value, it's going to be 1 and 1.67. Your gamma is nothing but, okay, your specific heat ratio, that is your Cp by Cv. Okay, so another thing is, okay, for the, depending on the medium, your R value is going to be, your R bar is a constant. universal gas constant, but molecular weight is going to be different for depending on the medium. So you have to substitute the molecular weight of the particular medium and you have to calculate. Sometimes what they will do is, okay, in the examination, gate examination, they will ask, okay, speed of sound in the CO2 medium or CO1 medium. For example, yeah, temperature prevailing at a Mars environment is something they are telling it as some 350 Kelvin. So the Mars environment is full of carbon monoxide or carbon dioxide. Okay, what will be your A value, speed of sound? If they are going to say that, okay, your R is going to be R bar is the universal gas constant. So R you can calculate from that, okay, for the particular value of CO2. Sorry, using a molecular weight of CO2, you can find out your R value, and also for a gamma value for a CO2 also normally they will give, okay, because we don't have any other means for calculating it, or otherwise we have to go ahead for your kinetic theory of gases. You need to see the degree of freedom. Based on that, okay, we can find, okay, n plus 2 by n using the formula. If you know the degree of freedom, you can calculate your gamma value. So now here your gamma is going to be function of your n, degree of freedom. Okay, so the degree of freedom is going to vary for your, I told you in the last class, for your degree of freedom is going to vary depending on whether the gas is going to be monoatomic, diatomic, or triatomic. Okay, so accordingly, what will happen if you are going to substitute the n value? That's going to result in your gamma is equal to 1 and 1.67. Okay. So people, chances are there, okay, they are going to ask you, okay, speed of sound in the, okay, Mars environment where the environment is going to be filled with your carbon dioxide, CO2, and they are going to tell that the temperature is going to be 350 Kelvin. You'll be in a position to find out your speed of sound value. Any question on that? Okay. Next is we are going to take a set of data, okay, and we are going to look at that, okay, is problem solving and all, okay, in terms of gate point of view. But I'm going to consolidate as a single problem, okay. If you have any issues, you can tell me that. So first thing is your thrust relation, your m dot a plus m dot e into your v, sorry, m dot a plus m dot f minus m dot a into your VA, okay, plus PE minus PA into AE. What we call this component of thrust is a moment of thrust. There is an expression for finding the thrust of an air breathing engine, for an air breathing engine. This is what we call it as your P minus A as a pressure thrust. Okay. So what will happen here? Based on the pressure thrust, whether the pressure thrust is going to be there or not. For example, if you look at your convergent nozzle, normally we will be using a convergent nozzle. Okay. In the case of your gas turbine propulsion. Okay. So here, if you look at that, your exit pressure is PE and PA. So first thing is, okay, while solving the problem, we'll be looking at that, okay, whether your nozzle is choked or unchoked. Nozzle is choked means the Mach number at the exit, okay, this point, it's going to be 1. Means at the throat, it's going to be 1, because throat is nothing but your minimum area, okay. So your mass flow rate is going to be maximum. So then only if the nozzle is choked, we are going to talk about that your pressure thrust. If the nozzle is unchoked, then what we call that your pressure thrust component is 0. So we have to look at only the your moment of thrust. Okay. If the nozzle is choked, if the nozzle is okay, let us finish off that. Okay, T is equal to m dot E plus m dot F. Sorry, m dot A plus m dot F. Yeah, m dot A plus m dot F into your VE minus m dot A into VA. So how we used to write it as, okay, we will take m dot A outside, 1 plus m dot F by m dot A into VE minus your m dot A into VA. So further we can write it as, okay, m dot A into overall, okay, your 1 plus F into your VE minus VA. This is your thrust, moment of thrust. So here F is, okay, m dot E, F by m dot E. What we call this one as a fuel to air ratio. Okay. So, okay, if the nozzle is choked, then the pressure thrust will be there. Pressure thrust will be there. Okay. So here the pressure thrust, okay, how there is a 3 type of pressure thrust will be there. One is, okay, you have a one is, okay, you have your under expanded nozzle, your over expanded nozzle, your correctly expanded nozzle. Sir, keep in mind that, okay, they are going to ask a question, whether your nozzle is going to be choked or unchoked in the exam and all. They are going to ask the relations, okay. So if it is nozzle is choked, what will be the mass flow rate at that at that point, okay, flow through the nozzle, okay. That and all you have to know about that. The mass flow rate is going to be maximum. What is the function of and all, we will see that one right now. Okay, so that we are going to see that right now. Okay, if the nozzle is going to be unchoked, automatically the pressure thrust won't be there. The pressure thrust is 0. Only your thrust is going to be only due to your moment of thrust. So if the nozzle is choked, automatically 3 kind of nozzle will be there. That is depending on your exit condition. Your P is going to be greater than PA. Okay, then the flow is going to be under expanded flow through the nozzle. So what we call that nozzle as an under expanded nozzle. So here your PE is going to be less than PA in the case of a over expanded nozzle. In the case of a correctly expanded nozzle, your PE is equal to PA. Means the pressure thrust is going to be 0 in this case also, correctly expanded nozzle. So here it's a positive thrust, but even after that also you are going to see that. Okay. So here we have to remember that if you look at that, okay, your nozzle is going to be like that. Sometimes if you look at the exit of the nozzle pattern, you go and open the YouTube and see that your jet exhaust, okay, in the rocket or in the your air breathing engine. So you can see a diamond-like pattern. Yeah, diamond-like pattern. Yeah, diamond-like pattern now. Okay. So here what is going to happen at the exit of the nozzle, a oblique shock is going to occur. Sorry. Expansion fan is going to occur. Expansion fan occurs. So if the flow through the nozzle, okay, if the exit of the nozzle, if it is going to P is going to be greater than PA, at the exit you can see a dotted line. So here. So what will happen? Expansion fan is going to occur. So this is what we call it as a free boundary. What we call this as a solid boundary. Okay. So what will happen? Okay, the exit only, it's your expansion fan is going to occur. So there is an unlike reflection of that. Keep in mind that in the exam they are going to ask, okay, in the free boundary whether reflection is going to be like reflection or unlike reflection. Unlike reflection means your expansion fan reflect as a oblique shock, and oblique shock reflects as a expansion fan. So what will happen? This process, okay, the unlike reflection is going to continue until the time, okay, your PE is going to be PA. Okay, so whatever the pressure here prevailing PA, here your PE, okay, that's going to be what will happen. So until the time of your PE is going to changes to PA, that's going to happen. In the case of a over expanded nozzle, at the exit you are going to have a oblique shock. So this oblique shock further, okay, same unlike reflection only. Okay, so here what will happen? Your oblique shock is going to be oblique shock reflects as a your expansion fan, your expansion fan reflect as a oblique shock. Okay, so it's going to be vice versa. It's going to continue until the time of, okay, you are going to have a same case. Your P is going to be changes to PA. That condition achieved. Until that, okay, that's going to happen. Okay, now we talked about the unlike reflection. What do you mean by like reflection then? What do you mean by your like reflection then? What do you mean by like reflection? Here, your oblique shock will reflect as oblique shock. Reflects as a oblique shock. Okay. Your expansion fan, same thing. Reflect as a your expansion. So that's what is going to happen. This is going to occur, your like reflection is going to occur in the solid boundary. In the solid boundary, okay, we are going to have a like reflection. Okay, so keep in mind that people are going to ask, okay, if you in the examination they are going to ask, okay, what do you mean by under expanded nozzle? What do you mean by over expanded nozzle? What do you mean by correctly expanded nozzle? What is the conditions for that? What will be the at the exit? What is going to form? Surely they are going to ask whether thrust is going to be positive or negative. You can decide from that what is going to happen in the interview and all. Surely they will ask. If you are going to mention that, okay, somewhere loose stock if you give, or they will ask surely. Any questions, sir? And also another thing is, okay, you are across the shock. If you take a normal shock, what will be the your P2 is going to be greater than P1. 2 is after the shock. Station 2 is after the shock. 1 is before the shock. Your T2 is going to be greater than T1. Your rho 2 is going to be greater than rho 1. Your P02 is going to be lower than P01. Your T01 is equal to T02. Your V2 is lower than your V1. And also, if you look at that, okay, if you look at the relation for this one, your P2 by P1 or T2 by T1, that is across a sock, they are going to tending to infinity when your Mach number, inlet Mach number tending to infinity. But your rho 2 by rho 1 tending to a finite value when M1 tending to infinity. Okay. And also, if they are going to ask you, okay, what is the governing equation for your sock theory, governing equation, okay, so you can say that your continuity equation, continuity equation, momentum equation, energy equation, and your entropy principle, and your perfect gas equation. That is, you are treating the gas as a perfect gas approximation. These are the governing equations. If you look at the continuity equation, rho 1 V1 A1 is equal to rho 2 V2 A2. Your momentum equation, it's going to be P1 rho 1 V1 square is equal to P2 plus rho 2 V2 square. Your this one H0 is equal to H1 plus V1 square by 2. That is equal to H2 plus V2 square by 2. Your perfect gas relation is P is equal to rho RT. So certainly they will be asking why, okay, you go and take your gas dynamics by Radhakrishnan or any other compressor book. Okay, they might have given a reason for that, why your rho 2 by rho 1 changing to a finite value when the M1 tending to infinity. M1 tending to infinity. So normally in the examination point of view, these things they are going to give a much priorities, because I started, okay, I went into that compressor flow, but anyway, you keep in mind that. But one difference between your normal sock and oblique sock is, okay, except the velocity, okay, the remaining things are going to be same. That is your, but the increase in static pressure is going to be coming out. If you look at the oblique sock, if you are going to have a weak solution, still, okay, your after the sock, okay, your Mach number is going to be a supersonic. So just look at that, okay, and even your stagnation pressure loss also, your stagnation pressure loss is less compared to your less when compared to your normal sock. Okay. Okay. Now we'll go into our topic now. So I mentioned about your choked flow. In the this one, I mentioned about your choked flow. So if you look at that, your m dot is going to be maximum. So if you look at that, the m dot, it's going to be your function of your P naught, T naught, your A star, that is your minimum cross section area, gamma, and your R. These are the function of that. So for example, we are going to have a fixed value of P naught, T naught, and A star, and your gas also not going to change. So automatically your mass flow rate is maximum. Okay, if you want to increase the mass flow, one thing is you have to modify these parameters for the particular exhaust. That is your P naught is your stagnation pressure, your stagnation temperature, and this is your throat area. Okay. Stagnation temperature. So keep in mind that it's going to be function of P naught, T naught, and A star. So something point for a air and all, okay, it's 0.623 like that, square root of RT naught. Some square value will be there. Okay, just go and check it up your compressible flow book by any book, Yahya or Radhakrishnan or Anderson. You refer that and get the relations. Surely they are going to ask you in the examination, okay, how we are going to calculate your mass flow rate or a choked condition. What would be the maximum mass flow rate? What is the relation for finding that? Please keep in mind that. And other thing is, okay, that we have to keep in mind that your m star. M star is the, okay, your velocity of the body divided by critical velocity of the sound. The advantage of that, okay, your m star, what we call it as, it's a characteristic Mach number. Characteristic Mach number. When the m tends to infinity, when the your m star is going to tending to a finite value. When the m tends to, when m is going to be subsonic, your m star also going to be subsonic. When m is equal to 1, that is sonic, okay, your m star also going to be 1. When m is supersonic, okay, your m star also supersonic. But when the m tends to infinity, your m star tends to, your characteristic Mach number tends to a finite value. Okay, so something for a air and all, something close to 2.48, 2.48, 2.6, like that it will be. See, the advantage of that, okay, you are going to have a, you know about shock polar. What do you mean by shock polar? It's a graphical representation of shock wave properties. Graphical representation of your shock wave property. Okay, graphical representation of your shock wave properties. So now what will happen if I want to have for a Mach number of going towards a infinity, then I need to have a lengthy seed that's going to explain about your shock wave properties. If I use Mach number. But if I am going to use a characteristic Mach number here, so automatically what will happen? I'm going to have a small seed. I can put everything together and I can keep it with me. That's what the major advantage of your characteristic. Okay. Okay. Then now we will go into your propulsion efficiency. Okay. And I'm going too much into that your compressor flow part. So we have seen your thrust relation. Okay. So once again I'll tell you about that. Okay, your T is equal to your m dot A into 1 plus F into PE minus PA plus PE minus PA into AE. This is a thrust relation. Okay, I'll come to the propulsion efficiency a little later. Okay, again your specific thrust. It's going to be your, that is what we call it as your TS. Okay, so T by m dot A. So it's going to be 1 plus F into PE minus PA plus PE minus PA into AE by m dot A. AE by m dot A. Sometimes people used to say that, okay, the thrust relation and all, okay, they'll be taking it as 1 plus F is going to be almost close to 1. The reason is, okay, your F is going to be very much smaller than your 1. So automatically they will be taking it as a 1 plus F as a 1. So automatically your thrust relation is going to be changing to m dot A into PE minus PA, okay, plus PE minus PA into A. That way also. This is for a idealized condition, very simple condition. Idealized condition here. So they will be asking about that, sir, your specific thrust relation. Next is your TSFC. TSFC is thrust specific fuel consumption. These and all they will be asking it in a 1 mark questions. Thrust specific fuel consumption. The thrust specific fuel consumption TSFC is nothing but your m dot f divided by your thrust. So we can write it as your f divided by your specific thrust. F divided by your specific thrust. How we return that? We can write it as m dot f divided by your specific thrust is nothing but thrust m dot a into your specific thrust. We can write it as. So this one further we can write it as m dot f by m dot a. We can write it as fuel air ratio your specific thrust. That's going to be your f divided by your 1 plus f into PE minus PA plus PE minus PA AE by AE by. So these are the 3 important relations: your thrust, specific thrust, TSFC, and also if it is in the thrust relation, under expanded nozzle, over expanded nozzle, or a correctly expanded nozzle, or a choked flow. So those things you have to be means you should not forget that. Same way you need to know like reflection, unlike reflection, and your correctly expanded. What is the conditions for that? You need to know. Same way, don't forget the speed of sound. How we are going to find out the speed of sound? R is nothing but your gas constant. It's not a universal gas constant. R is going to be R bar divided by molecular weight. R bar nothing but your universal gas constant. So next is we'll go ahead for the the propulsion efficiency. So here what we define is your propulsion efficiency is going to be related to your thrust power to the your whatever your kinetic energy of the exhaust cell. It's going to be it's going to be related to your kinetic energy of the exhaust jet. So here if you look at that is a radiation. According to that, this is going to be VA, this is your VE. So same way. So we can write it in our form m dot into VA. So they took a case of your 1 plus f as they took it as 1. Minus PE minus PA divided by, that is your thrust power divided by kinetic energy of the jet. Your m dot a into your PA into your PE minus PA plus PE minus PA whole square. So this is going to be talking about that your kinetic energy of that is jet is coming out. If you are going to simplify that, m dot a cancels out. So finally you are going to have if you are going to simplify that 1 plus PE by. So now when my propulsion efficiency is going to be 100%, because we are going to look for a 100% specific efficiency when your VE by VA is going to be 1. VE by VA is going to be 1. But is it possible? for your propulsion efficiency is going to be 100%. If you look at your thrust relation, okay, for a simplified case, m dot a into your PE minus PA. Let us have a unchoked nozzle. So what will happen? Your thrust is going to be 0, tending to 0. So practically it's not possible to have your propulsion efficiency at 100% in the case of your gas turbine engine. Okay, so these are the parameters you have to know about your this one. Okay, and another thing is, okay, you need to know that your function of your intakes and nozzle. Already last class I explained about that. What do you mean by your intakes and nozzle? It's going to do. Okay, so here you got to know your efficiency of the intake, isentropic efficiency of the intake. Okay, that we will be looking at that. Okay. So this is going to be your A and this is going to be 1. This is your intake. What's it's doing? Okay. Whatever sorry, this is a nozzle. Sorry. So it's going to be your intake. So this is your A and this is your 1. Okay. So here what is happening? Okay, your M infinity. So you need to know that, okay, your velocity is going to decreases, your pressure is going to increases. Basically, it's a pressure recovery. That is, we are going to convert the kinetic energy into pressure energy. Okay. Now, what you can do is you take your Hill and Peterson book. Okay, your Hill and Peterson book. So an intake diagram will be there. Okay. So if you take your diverging cross section, basically this is nothing but your diverging section. So diverging section means what will happen? There will be if you are not going to maintain a proper diverging angle, okay, your 2 alpha, if you are not going to maintain, okay, something close to 20 or 21, or some people they used to mention is a 14. Okay, so 2 alpha, if they are not going to maintain close to your 21. So what will happen? There will be a boundary layer separation in the valve. So it's not going to do the purpose of you are converting a kinetic energy into a pressure energy. You are going to get as a jet-like flow. So this phenomena is going to be caused due to your boundary layer separation. So you refer, okay, your mechanics and thermodynamics of propulsion by Hill and Peterson. Okay. So in the section, okay, these are your sections, okay, your solid area, intake area, your diverging area. What are the prominent location of boundary layer separation? What are the prominent location or locations susceptible for your boundary layer separation? Prominent location for boundary layer separation. So please keep in mind that, okay, please go through that. Still, if you couldn't find out, you have my number. or you have my email ID, you can send a mail to me, or you can send a WhatsApp message to me. I'm ready to clarify for that. Okay, so please go and refer, because we have a very limited time. In the very limited time, it's very difficult for me to cover each and every things. Okay, so just go through that. Still, if you couldn't understand, please tell me. I'm ready to take it up in the next class. Find out that. And another thing is, why there is a boundary layer separation. This you should have studied in your basic fluid mechanics and boundary layer chapter. Okay, why there is a boundary layer separation? What do you mean by adverse pressure gradient, favorable pressure gradient? Okay, and you got to know about that. Other than that, for example, if I have a curved surface, your boundary layer is going to separate. So, what is the value of your dou square u, your dou square tau by dou x square? Or some of the parameters are going to be there. Okay, at that point, what will be the values of that? If you refer, okay, some of the boundary layer separation part, I think fluid mechanics by Kumar or Bansal, or Bansal I won't recommend, but anyway, that's going to be simple for that. Okay, your those things. Okay. So accordingly, we can look at that. Okay. So if you refer that, they are going to take tell the values of that one. Your boundary layer separation. What will be the your dou p by dou x? What will be the value of dou p by dou x? Dou square u by dou x square. So these values, how it is going to change at the point of separation. If it is your boundary layer is going to be reattaches, what will be that? If it is a turbulent boundary layer, a laminar boundary layer, where will be the boundary layer thickness will be higher? Why? Boundary layer thickness, which case it's going to be higher? How energy exchange is going to be there in the laminar boundary layer? How the energy exchange is going to be the turbulent boundary layer? What is the critical Reynolds number for your laminar to turbulent transition, for your flat plate, circular cylinder, for your boundary layer separation, critical Reynolds number for those things and all. Just check it up with that. How the boundary layer profile for a laminar to turbulent. Fully, what do you mean by fully developed flow? Because I can't teach all those things here. Okay, I'm asking you to prepare this one. It's going to be useful for you. Still, if you couldn't understand, you can come back to me. I can send the notes to you, or I can explain to you if you are coming to me. Because I got a set of aims. Okay, I need to go ahead with that. Okay, so certainly they are going to ask a question on that. Okay, your boundary layers and all. Okay, so please keep in mind that. Okay, and also one more thing that you have to remember is your different types of three different types of your boundary layer thickness. So your moment displacement thickness, your momentum thickness, and your energy thickness. How these three parameters are going to be? Even you can refer aerodynamics by glancing. Or like your Hill and Peters, Cotton and Carpenter. Aerodynamics for engineers by Cotton and Carpenter. those books are going to give the provided information for displacement thickness, momentum thickness, energy thickness in detail. Okay, just look at that. But the main thing that you have to know for our present our discussion, okay, what are the prominent location? This location, this location. Okay, so you identify proper terminology. Keep in mind that. Okay, now let us go for a isentropic efficiency of the intake. We can put I or D, anything. Diffuser also, you can do that. Okay, the definition for that, it's going to be T01 dash. That is because here what is happening is a compression process. Okay, T01 dash, that is your isentropic work transfer by actual work transfer. Okay, your T01 minus T. So once they have asked this relation in the gate examination, please keep in mind that this one. So don't forget your isentropic efficiency of compressor, isentropic efficiency of the turbine, your isentropic efficiency of the intake, isentropic efficiency of the propelling nozzle. Okay, so these relation you keep in mind that even your transmission efficiency also, your work transfer relation for the turbine, work transfer relation for the compressor, even whatever your parameters, performance parameter we have seen until now, those things. Okay, so now already we looked at that for the gas generator. We looked at that. Okay, so from these we can write it as your T01 minus TA is going to be your T01 dash minus TA divided by your isentropic efficiency of the diffuser. So we can take a TA outside. Okay, so by your isentropic efficiency, your T01 dash by TA minus 1. So this is your TA by TD. We can so how much amount of your temperature rise and all we can do that. Or otherwise, what we can do straight away, we can have the relation for your P01 by PA as okay. P01 by PA as 1 plus eta I into gamma minus 1 by 2 or eta D gamma minus 1 by 2 m infinity square to the power of gamma by gamma t square. So flow through your diffuser is going to be an adiabatic. Okay, T01 by TA is equal to 1 plus gamma minus 1 by 2 your m infinity square. You can use straight away this relation. So now you look at your diffuser. Okay, so you look at your diffuser now. What is it's happening? Okay, if you, I know that okay, which Mach number it's flying, and I know that your PA, TA. Okay, from that I can this. Let us take this as a condition here. This is a condition here. Now I can find out my P01 and T01. Already we did it for your compressor, combustion chamber, turbine, and you can do that very easy. Same way we can do it for the your propelling nozzle also. For the propelling nozzle, already I talked about that. Okay, your case is okay. You refer page number in the 9th edition of your Hill and gas turbine theory, Cohen and Roger. You refer page number 1022. Okay. 111. Okay, refer gas turbine theory. Okay, if you want to more about your theoretical aspect. Okay, gas turbine theory by Cohen and Rogers. 1012, something close to 110. Okay. Page number. These page number, if you refer that, you are going to get a lot of theoretical insight. So that's going to help you in understanding your concept-based question that's going to be asked in the gate examinations. Why we have to choose a convergent nozzle instead of a convergent divergent nozzle? What do you mean by thrust reversal? What do you mean by variable area nozzle? What is the requirement for that? Those things and all you can understand from that. Okay. So now we look at that your propelling nozzle. Your isentropic efficiency for the propelling nozzle. So if your nozzle is going to be a convergent portion, so what we can take it as, okay, this is a station 4, this is a 5. Okay. So in that case, your propelling isentropic efficiency, the propelling nozzle is going to be here. It's an expansion your expansion process. Okay. So actual work transfer by isentropic work transfer. Your T04 minus T5 divided by your T04 minus T5 dash. So you can find out your T04 minus T5 from these relations. So what is the use out of it? So T04 minus T5. So if you look at that, okay, your H04, okay, whatever this one, we can write it as H5 plus V5 square divided by 2. The V5 is nothing but your VE. So we can write it as H5 plus VE square by 2. So exit velocity. So we can write it as V is equal to square root of, okay, your H04 minus H5 to 2. So further this one we can rewrite that as a your square root of, okay, 2 Cp T04 minus T5. So for example, if I am going to give your whatever the temperature T04, this is nothing but, okay, your turbine exhaust temperature, stagnation temperature, at the exit of the turbine. Okay. So if I know that, and if I know my T5, so automatically I can find out my T04 minus T5. Okay. So even we can, if you know that these things, we can write it as in this form. Your V is equal to square root of 2 gamma R by, because Cp is equal to be gamma R, right? Gamma minus 1 into isentropic efficiency of the nozzle into T04. And if you know that pressure drop across the nozzle, okay, so then we can write it as, okay, T04 by P5 so I can find out my exit velocity. So this your P04 by P5, okay, if you look at that, the pressure drop, okay, so this is going to be talking about that whether your nozzle is going to be choked or unchoked. If it is your nozzle is going to be choked, it's going to be your P04 by, okay, your P stop. That's going to be the pressure issue here. If it is unchoked, we can keep it as such. Okay. So we have to find out your critical pressure ratio. Okay. How will you find out that your critical pressure ratio? Okay. So for that, first we have to know that your critical pressure ratio across the nozzle. Okay. We can find out using this relation. You can use this relation to get that your P04 by PC. PC is here nothing but, okay, your P stop at the exit. And also from our known condition, we can find out your this one. Okay. Any questions, sir? Excuse me, any questions? Any questions, sir? Okay, good. So right now what I'm going to do is, okay, I'm going to give something close to 10 questions to you. So based on whatever the point we have seen now, okay. So don't discuss with others. Whatever the answer you know, just write it. You take a 10 minutes time. You write the answer for those questions, okay. Write the answer for those questions and keep it with you. I'll dictate the answer for you. So then you can understand yourself, okay, how much you have followed for that. It's very really so basic, okay. So but mainly this is based on from your last class, this one. Okay. So these are your 10 questions, okay. Just take 10 minutes time for you, 5 to 10 minutes, okay. We will see that. We will discuss the answer for these questions, okay. Just is two basics. Maybe sometimes maybe a concept based question may be asked similar to that. Just in a piece of paper, think and note down the answer A, B, C, like that. Have you done with that? Excuse me? Have you done with that? Excuse me. Have you done with that? Okay. For the first question, the answer is okay. Your large acceleration, your smaller mass of the air. Second question, hot section includes okay the basic aspect two main section, hot and cold. The hot section includes combustion turbine and the exhaust. The third question, the jet engine derives the thrust from the reaction of hot propelling gas. So the working fluid of a gas turbine is your air. And the fifth question, which statements are true regarding the aircraft propulsion? The engine driven by propeller imparts relatively small amount of acceleration to large amount of air. Sixth question, at what point an axial flow turbojet engine will the highest gas pressure occurs? At the compressor outlet. What section provides proper mixing of fuel and efficient burning of the gas? Combustion section. Of the following, which type would most likely have a noise suppression unit? Your turbojet, because that's going to produce more amount of noise. We need to have a noise suppression unit. The pressure of a supersonic air as it flows through a divergent nozzle, what will happen? Divergent nozzle. It's going to decreases. You look at the AV relation over there. A high bypass engine results in what will happen? Overall slower airflow, greater propulsion efficiency. So check your answers, how much question you have done it correctly. So beyond that, how much you have studied, how much you have to prepare more. That's going to help you. Okay. So still, if you need more clarifications, I'm ready to look into that. If you want anything more, okay, regarding okay, if you want to have any other more test, I'm ready to flutter questions to you. You work on that and look that part of it. Good, very good. Okay. If you want, you can write a mail to me. I'm ready to share more questions with you. Okay. So right now, what we are going to do is we are going to take a data for the simple turbojet. Okay, and we will see that okay how we are going to solve it. So basically a problem from your gas turbine theory by Gordon Rogers only. Okay. So here we taken a simple turbojet. Okay. This is the your first thing that you have to do is, okay, you draw the your TS diagram for that. Because here we are going to deal a condition with ideal cycle with losses. So keep in mind that if you understand this problem properly, okay, then you can solve anything related to your turbojet. You can solve anything related to your turbojet. If they are going to give, for example, okay, the pressure recovery through your diffuser or through your intake, if you want to find out, you can easily find out very easy how much amount of pressure recovery. So your P02 by your PA, sorry, P01 by PA, because they are going to give the intake efficiency. We have the relation, or how much amount of your work required for running the compressor, that also we can calculate, or how much amount of work provided by the turbine, that also we can calculate, because we have the your polytropic efficiency, sorry, your mechanical efficiency and your work compressor work output, work input. So that's we can find. Or if I want to find out my F, the fuel air ratio, that also I can find out. Can we go ahead? Are you okay? Okay. So we are going to solve this problem. We'll make sure that we are going to answer any questions related to your simple turbojet. So at the end of the session, okay, I'll have a one or two problems, okay, a detailed problem that is required for your turbojet. I have it, okay. I'm going to share it with you. I'm going to share it with you. You work on that, okay. You work on that, and if you have any issues, you tell me. I can solve it. I can capture it as a video. I can put it in the YouTube. You can see that one. That's not a problem. Okay, so we are going to solve the problem. We are going to finish the whole process. Or at the end of the problem solving, okay, you ask a question. I am ready to clarify your your question related how you are going to solve this one. Any question, if you observe these questions properly, okay, you can solve any problematic questions. Okay. Let us have your this one. First is, okay, we know that, okay, here itself we can see that your intake. So first is, we know that your Mach number is going to be, what is the Mach number? Your 0.8. Your M infinity is 0.8. And we know the PA condition, and they had given the even A also. So they are going to reduce your work. So what we can do is, your T01 by TA is going to be 1 plus gamma minus 1 by 2 M infinity square. So let us take a gamma as a 1.4 here, because here gamma A as a 1.4. Okay, gamma G we will be taking it as 1.33. That is your hot gas, gamma value of the hot gas, we will take it as 1.33. So now we know that your Mach number, we know your TA value, we can calculate your P01 value. Any question on that? If you have any questions, please ask me. Your P01 by PA, already we have seen the relation here. We have discussed here. Where is that one? It's going to be 1 plus isentropic efficiency of diffuser divided by so here we know that, okay, let us take it as this is I. Okay, isentropic efficiency of diffuser we know, we have the value here 0.93, and we know the gamma value, we know the M infinity, we know the PA, we can calculate your P01. Even people are going to ask how much the percentage of pressure recovery. Okay, you can easily find out that. Okay, so how much percentage of pressure recovery? So you know the P01 here, but you know the P0A by PA is equal to 1 plus gamma minus 1 by 2 your M infinity square whole to the power gamma by gamma minus 1. You know the PA, you can calculate your P0A. So your P01 minus P0A, okay, so that's going to talk about that. Okay, this much amount of value, or if you want to have that, okay, your P0, this much amount of percentage of your P01 is going to be like a pressure recovery. If they are going to ask a pressure recovery, you can do that. Okay. The second part is, okay, we have a your compressor. Okay. We did it with the your intake one. So we know that, okay, your T02 minus T01 is equal to that we have already derived. Okay, you refer your yesterday's class notes. T01 divided by isentropic efficiency of the compressor into your compressor pressure ratio whole to the power gamma minus 1 by gamma minus 1. So here we know the compressor pressure ratio. They are given the your compressor pressure ratio. You know the isentropic efficiency of that your compressor. So substitute, we know the T01 value. Already we have calculated. So we are going to get the your T02 minus T01. We can calculate it. Now we can go for your work done required for the compressor for a unit mass flow. You can do that Cp into your T02 minus T01. This much amount of percentage of work is okay, per unit mass flow. And also how much amount of pressure at the exit of your compressor, that also we can find out P02 by P01. Compressor pressure is your times your P01. Already we know the P01, so we can calculate it. So now we need to know one more thing here. Okay. Even we can calculate your T02 also. T02 is equal to your T01 plus T02 minus T01. Already we know that, okay, we can calculate that. So your turbine and compressor, they are going to be connected by means of a single shaft. We know that. Already we looked at that your gas generator part, your compressor and turbine, they are going to be connected by means of a single shaft. Okay. So whatever your turbine work, okay, work required for the turbine, it's going to be equivalent to, okay, compressor work divided by your transmission efficiency. So now across the turbine, okay, the temperature drop, okay, your for a unit mass flow, okay, CPG into T03 minus T04, because temperature drop is going to be there, is equal to your CP into T02 minus T01 divided by your this one. So further this one we can write it as, okay, your T03 minus T04 as, okay, your this is CPA into T02 minus T01 divided by your CPG into your transmission efficiency. This is your nothing but your transmission efficiency, mechanical transmission efficiency. Because your compressor and turbine are connected by means of single shaft, there will be a gear will be involved, okay, there will be a vintage loss, friction loss will be there, something close to 99% will be taking it as. Even if you refer your problem statement here, you can find out your 0.99%. So now, and also they are going to give that, we know that now, we know that T02 minus T01, CPA is, okay, CPA, value of CPA is going to be 1005 and CPG is 1148. Joule per kg Kelvin, and this is CPA, CPG is 1148 joule per kg Kelvin. So if you substitute it, you can get the your T03 by T04. So your T03 is nothing but your turbine inlet temperature. Sometimes they used to say that engine gas temperature, EGT. Normally what they will say that, okay, sometimes they used to call this turbine inlet temperature some EGT, that is engine. So we know the T03 and we can calculate your T04 is equal to, okay, your T03 minus T03 minus T04. So you can calculate your T04. Okay. And other than that, okay, if you look at that, okay, we need to know that your P03, that is your pressure, chamber pressure at the exit of this one, your P02 minus, okay, delta PB. That is, this is going to be your combustion chamber pressure loss. So normally they will be giving it a certain percentage of your compressor delivery pressure. Okay, it's going to be your 1 minus your P02 into 1 minus whatever the your value, that is 4% or 5%, whatever the one. So you can calculate your P03. Now, okay, we know that, okay, let us go into the your turbine part. Okay, your actual work transfer divided by your isotropic work transfer for the your turbine minus T04 your T03 minus T04 divided by your T03 dash minus T04. So they had given the your isentropic efficiency of the turbine, and you can calculate your T03 minus T04. Here the known value is isentropic efficiency and your T03 minus T04. These two things we know that. Okay. So then we need to find out your T03 minus T04 is equal to 1 by isentropic efficiency into T03 minus T04. Sorry. Your T04 dash. So now we can find out your T04 dash, okay, from these is equal to your T03 minus 1 by isentropic efficiency of the turbine into T03 minus T04. So we know that, okay, we need to find out the pressure at the exit of your turbine. So P03 by P04 is going to be T03 by T04 dash whole to the power gamma by gamma minus 1. Here gamma is nothing but your gamma G. Let us take it as 1.33 because it's a hard dash. So we know that P03 we know, T03, T04 dash we know. We can get your P04 here. You can get the P04 here. Any questions, sir? Are you okay? Once again, I will repeat you. Please look at that. First is, okay, we know that, okay, from the inlet conditions, we can get your T01 value from the isentropic relation. T01 by Ta is equal to 1 plus gamma minus 1 by 2 m infinity square T01. Even we can write it as this one as your T0A by Ta, which is equivalent to T01 by Ta, because your flow through your intake is going to be a adiabatic compression. Okay, so adiabatic means T0A is equal to T01. That's why I can write it as T01 by Ta. So I can get the T01 here, and from the here adiabatic compression, it's not a isentropic compression. So P01 by Pa is equal to 1 plus your isentropic efficiency times this one. You can calculate your P01. Even this method you can adopt for a pressure recovery for the diffuser. So this relation we already calculated for the T01 by T02 minus T01. That is how much amount of what we call this one as your stagnation temperature rise across the compressor. So that's going to be T01 divided by isentropic efficiency of compressor, this one. So now your compressor is going to be work done for the compressor, you can calculate it. Your compressor and turbines are going to be connected by means of a single shaft. Okay, we can get your how much amount of this is going to be your temperature drop, stagnation temperature drop across the turbine. So from this, okay, we can get your T04. So from the combustion chamber, we know that P02 at the exit of your compressor, you can get your P02 value, because we know the compressor pressure ratio, we know the inlet to the compressor pressure, stagnation pressure. From that we can get your P02. But in the case of Brayton cycle here, we are not going to treat perfectly and constant pressure heat addition. It's going to be a certain pressure loss will be there. So that's what we are taking it as delta PB. So we are going to get your P03. And also this is your isentropic efficiency of the turbine. Okay. T03 minus T04 divided by T03 minus T04 dash. So you know that, okay, your isentropic efficiency of the turbine we know, T03 minus T04 we know, we can calculate your T03 minus T04 dash. So from that we can calculate your T04 dash. You know the remaining parameter using isentropic relation, you can get the your T04. So now the nozzle pressure ratio is it's nothing but your P04 divided by PA. PA is whatever the pressure here divided by whatever the atmospheric pressure. So now we have to see that whether your nozzle is going to be choked or unchoked. Nozzle is choked or unchoked. Okay. So for finding that, okay, we need to find out that your P04 by for the PC for the particular this one. Okay, let us take it as a P star. Okay, so that's going to be this is a relation. So we can calculate your instead of PC, you can take it as a P star also. Okay, if you want, you can keep it as a PC. You know your this one isentropic efficiency of the nozzle, it's given here. If you look at that, okay, it's given here 95%. Okay, substitute it, get the value. For this problem, okay, if your P04 by PA is going to be greater than your P04 by PC or a P star, so then the nozzle is going to be choked. If the nozzle is going to be choked, what will happen at the exit? Your Mach number is going to be 1, 1. So the conditions are going to be critical condition: P star, rho star, and P star. We have to find out your critical condition here. We know that, okay, your what is the condition? Your P04 by TC is going to be gamma plus 1 divided by 2. Same way, your P04 by PC is going to be gamma plus 1 by 2 whole to the power gamma by gamma minus 1. And here we have to find out, we know the P04 and T04, we have to find out your TC and your PC. That's nothing but, okay, your T5 and P5. Your rho 5 is going to be P is equal to rho RT. Okay, P, your PC divided by, so rho C is equal to PC divided by RTC. Your R value is 287 joule per kg. So make sure that every units are not going to be in the kilo or mega and all. Okay, keep it in a basic unit. Substitute that, you can get the your rho C here. And also at the critical condition, what will happen? Your velocity of the body, okay, your VE is going to be your A, because M is equal to 1 square root of gamma RT C. You know the C, you can calculate that. So now, okay, you can calculate your mass flow rate is going to be rho C, A star, and your VE. You can calculate the X mass flow rate. So another important thing that you have to know here is, okay, your already we discussed about that your fuel air ratio, that is F. Your M dot A, your CPA, T02, this is T03, CPG, here M dot A plus M dot F. So this is your, here we are going to spray the fuel. So if you do the energy balance analysis, okay, M dot A, CPA, T02 plus M dot F into Q, okay, calorifically of the fuel is equal to M dot A plus M dot F, CPG, T03. Even if you want, okay, in the last day one class, whatever the one we have written. So this is the value, F value. CPG T03. This is the one we are going to get. Your F. F is here, nothing but okay, your fuel to air ratio. So now you go for the your thrust, specific thrust is nothing but thrust divided by your m dot a. Your TSFC is nothing but okay, your m dot f divided by t. So that one we can write it as f by your specific thrust. That's all. It's over. Everything is over. Any question? Any questions, sir? Any question? Just to take a few minutes time, okay? Just look at that stage by stage. You might have scribbled some notes, okay? Have a 5 minutes time, go through that. If you have any issues, please tell me. I'm ready to clarify that. I'm ready to give a 5 minutes time for you. Any questions, please discuss with me, sir. If you have anything, so whatever the point, okay, last maybe yesterday, last class 2 hours, this class more than 1.5 hours. So we have discussed. So if you have any question related to that also, you can ping me, or otherwise unmute and ask question. just draw a flow chart. Okay, what we are going to do? Okay, we are going to do first for the intake, then compressor, and compressor and turbines are going to be connected by means of a single shaft. From the compressor work input required, we are going to do that how much amount of work output provided by your turbine, that are going to be calculated using your transmission efficiency. In addition to that, then you go to the combustion chamber, how much amount of pressure loss is going to be there in the combustion chamber. Why there is a pressure loss? Because what will happen, whatever your only 30% of air is going to be passing through the central zone, remaining 70% is going to pass through your liner passage. It's mainly for cooling the flame tube as well as for effective mixing of fuel and oxidizer, okay, those purposes. So because of the mixing process, there will be a pressure loss will be there. That's what 3%, 4%, 5% they used to mention that of your compressor delivery pressure. Then, okay, already they are going to give an input parameter as a turbine rated temperature. We know the isentropic efficiency of the turbine. So if the process is going to be treated as an isentropic, what is your stagnation temperature rise? Stagnation temperature drop. From that we can calculate what will be the exit at the exit of your turbine, how much amount of your stagnation pressure. Then we know that the nozzle is going to be exit into the atmosphere where your pressure is going to be PA. So see that how much amount of that. From that we will see the nozzle pressure ratio, that is your P04 by PA. And we are going to find out that your critical pressure ratio for the particular nozzle, for the particular isentropic efficiency. Whether your nozzle pressure ratio, if it is going to be higher than the critical nozzle pressure ratio of the particular nozzle, then your flow is going to be choked. Using a choked condition, we get the value of these parameters, your VEP, rho C, and other things at all, critical conditions. From that, we can estimate that your thrust, your specific thrust and all here. Okay, we are going to have, okay, it's going to be 1 plus F into your VC, here VE, minus your VA. Okay, this is your momentum thrust, and your PE minus, okay, PE is nothing but, okay, PC by PA into AE by M dot. AE by M dot, okay, AE is the A star. So that we can write it as, okay, from these AE by M dot as a 1 by rho C into your A. So you know that your specific thrust and your TSFC is nothing but F by your TS. F and all you can calculate it from using this relation. Just what I did is I took whatever the example problem available in your Cohen and Roger, I solved it for your own understanding completely. I added whatever the necessary information required for that, I gave that thing to you. Even here, if you know that your M dot, if you want to find out M dot F, fuel flow rate, okay, if you know your M F and your mass flow rate of the air, from that you can calculate your F value. Or otherwise, if they are going to give the thrust, you can calculate your TS. If they are going to give your T value, okay, using this T value and TS value, okay, you can get your mass flow rate of the air, and you substitute it back here, okay. You are going to get the mass flow rate of the fuel, how much amount. Any questions, sir? So next is we are going to talk about that certain combustion phenomena. That is, that phenomena is very, very important for the your combustion chamber. So first thing is your premix flame and your diffusion flame. So the premix flame, what will happen if there is a molecular level mixing between the, that is, if there is a molecular level mixing between the fuel and oxidizer, the flame that you are going to get out of it is called as your premix flame. Diffusion means there is no molecular level mixing. There is no molecular level mixing between fuel and oxidizer. Then the flame is called as diffusion flame. The premix flame and example and all, something close to, if you look at that, your partially premix flame is your Bunsen burner. Or otherwise, sometimes what we call it as your double base solid propellant, what we call it as whatever the flame we are going to get it. Okay, the double base propellant, the flame is going to be a premix flame. But in the case of a diffusion flame, your oil wick flame, நம்ம வீட்டில் ஏற்றுற விளக்கு oil wick flame, your candle flame, okay. Sometimes firing the your, even we can't say that you are burning of firewood and all. So these are the example of your premix flame and your diffuser flame. Okay. So if people are going to ask, please don't forget that. Okay, what do you mean by premix flame? What do you mean by diffuser flame? So for example, if I have a your flame tube, okay, if I have a fuel air mixer, fuel to air mixer, okay, that's going to pass through, your flame is going to form. Okay, so whatever the flame that is going to be, your fuel air mixer is going to be moved towards that, your flame front is going to be traveling towards your flame front is going to be traveling towards the unburned fuel air mixer. So how fast your flame front is traveling towards your unburned fuel air mixer, that's what we call it as a flame speed. That is, how fast your flame front that is traveling towards your unburned fuel air mixer, that is called as your flame speed. Okay, we call it as a flame speed. Okay, so here another two more things that we have to keep in mind, your flashback and blow off. So these questions and all, they are going to ask, what do you mean by flashback, what do you mean by blow off, what do you mean by flame speed, what do you mean by premix flame, diffusion flame, what is example of that, they are going to ask in the concept based questions. Please keep in mind that. Okay, so now let us look at that. Okay, your unburned fuel air mixer, if it is going to be, it's having your velocity of that and your flame front velocity. Okay, so if your flame speed is higher than your velocity of the unburned fuel air mixer, so then what will happen? Okay, if the flame speed is higher than your unburned fuel air mixer, automatically the flame travel into the your fuel chamber. So that phenomena, what we call it as a flashback. So what will happen if the flame is traveled into your fuel tank? Your fuel tank is going to burst. And reverse of that, if the flame speed is lower than the onboard fuel air mixer velocity, then the flame is going to be thrown out of the flame tube. Flame is thrown out of the flame. So take a case of a Bunsen burner. If the flame speed is higher than whatever the incoming mixer, your flame will be travel into your flame tube, and it will go penetrate into the fuel chamber, storage chamber. That's what your flashback. Blowout is okay. If the flame speed is lower than the unburned fuel air mixer velocity, your flame is going to be thrown out of your flame tube. Flame is going to be thrown out of your flame tube. So that's what is going to happen in the case of your blowout. So here we have to remember a few things here. Okay, so we have to know premix flame, diffusion flame, your flame speed, and your flashback and blow off. Okay. Next, we are going to define a parameter called your equivalence ratio. According to equivalence ratio, we will be denoting it as a pi, that is your fuel air ratio divided by actual fuel air ratio divided by fuel air ratio. Okay, so if your pi is going to be less than 1, what is called as fuel lean mixer. If pi is equal to 1, what we call it as a stoichiometric mixer. And your pi is going to be greater than 1, what we call it as a fuel rich mixer. So the adiabatic flame temperature, what we call it as P, that is a maximum possible temperature. Adiabatic flame temperature, that is a maximum possible temperature. If I look at that, the variation of adiabatic flame temperature, okay, for a hydrocarbon mixer, so your pi is something, okay, 1. So your T adiabatic, okay, it will be going towards that its maximum. You can see a maximum of your adiabatic flame temperature close to your pi is equal to 1. Okay, so how will you find out your stoichiometric fuel air ratio? So let us take your methane that's going to react with your oxygen. Okay, assume that, okay, here while doing that, okay, just I took a case of a simple case, but air and all there will be a different. Okay, so next class I will take up that. Okay, CO2 plus 2H2O, so 4H, okay, 2O, 2O, 4O. You have to balance that, and you have to find out that your fuel air ratio now. Fuel to air ratio, your molecular weight of your CH4 divided by your molecular weight of 2 into molecular weight of oxygen, because 2 moles of oxygen is going to be there. That's going to give your fuel air ratio stoichiometric. So if you are going to have an oxygen bonding, if it is a air bonding, air for a air, there will be a molecular weight will be there O2 plus 79 by 21 N2. Okay, so you have to do that. Okay, CO2 plus H2O, okay, plus your 79 by 21. 1 minute, be on the line. Come inside. Good on. Yeah. Okay. So, any questions, sir? Any question? So in the next class, we'll continue with that. Okay. We are moving ahead. Okay. We'll take a certain case. How will you find out your pi value for certain fuel? Because that's essential for in terms of your gate examinations. So you need to find out. They will ask you to find out pi, and also they will ask you to find out theoretical air, percentage of theoretical air, percentage of excess air. Okay. So then whether you have to know whether your pi is equal to less than 1 fuel lean mixer, pi is equal to 1 stoichiometric, pi greater than 1 fuel reach, your equivalence ratio formula. For certain fuel, you can find out stoichiometric fuel air ratio. So those things you have to know. We'll continue in the next class. If you have any questions, we can discuss further. So if you have any specific question on that, okay, whatever the problem we have solved in turbojet, please write a mail to me, or with this one, I'm ready to sort it out there. Because the moment if you are not going to open your mouth, I assume that okay, you know everything, you understood everything. That's what my assumption is going to be. Because you didn't ask any question, I assume that okay, you understood everything. Sir, I used to assume that okay, if you're not going to ask any question, you understood everything. That's all I'm going to say that. If you are going to ask a question to me, if you are going to write a mail or write a message to me, if it is so urgent, I'll call you and tell you. If not, I'll take that in the next class and I can show you. If it is so lengthy, I can scribble it in the paper, take a photo and send it to you. That's all I can do. Very easy. That's not a big task. My interest is something different. Keep in mind that. Don't think that whatever the money I am going to get it from the college, I am going to take the class. Each and every day from my teaching, I am learning a lot from you people. If you didn't ask any question, I feel that I'm not going to learn anything from you. Because you didn't ask any question. If it is an easy question, I can answer. If you are going to ask some question, if I don't know, I'm going to read that again. I'm going to learn something different. I'm not going to give any internal mark for you. I'm not going to give any other things for you. I'm nowhere related in any of the process, your academic process. So you should not have any hesitation in asking questions. Anything, sir? Any change you are expecting or anything? Because I am going to take another 2 hours class next Thursday. You can ping. You can put a message to me if you need anything. Next class I'll take up a bit about. If you want, I can take up the turbofan problem, or otherwise I can go to rocket propulsion. Better I can go for a rocket propulsion. Any questions in the comment column? It's all, sir. I done with my things. Okay. Okay, so I done with that. We will meet again on Thursday 4 to 6. Okay, so we can take up if you we'll continue little bit on your equivalence ratio and theoretical air. Okay, and we'll go ahead for rocket propulsion. Or if you want anything more, please inform to your class instructor. Okay, Arun. Then we will see them. Okay, thank you.